RickyNilsson from the Department of Astronomy and the Astrobiology Graduate School of the Faculty of Science. And we've chosen the topic circumstellar debris and its impact on life, a solution to the Fermi's paradox. And this is just to get started.
Okay. Yeah, so I will talk about debris and its impact on life, both in the sense of its effect on life and the actual physical impact on life, and the relation to the Fermi paradox. So I will start by saying something about, just briefly about the formation of a planetary system, and including circumstellar debris and how it is observed. Then I will talk about some general statistical results that have been derived from the large surveys on debris disks, and also where the solar system fits in this picture. So, and then I will talk a bit about impacts and extinction, both well, past events and the current threats in the solar system. And then in the end I will say some words about the Fermi paradox. Well, most of you have probably heard this before, but the current model for planet formation looks something like this. If we skip the details, that we have a collapse of cold molecular cloud that fragments and produces several spinning protostellar disks. And this evolves into a protostar surrounded by a protoplanetary disk. And in the disk we have a gradual build-up of small particles into larger fragments by sticking and collisions. And within 10 million years, planets have formed. At least gas giants must have formed within 10 million years, because within that time all the gas is gone from the system. The terrestrial planets might have another 100 million years or so to form. And we're also left with these belts of debris, or leftover planetesimals, which is then asteroids and comets, basically. And they continue to collide in these belts and produce dust. So these belts are called debris disks, or debris belts then. And they are detected by observing the excess of far infrared and sub-millimeter radiation compared to a pure stellar photosphere. So this is just one example then of a star where you see you can fit these flux points with a stellar photosphere, but here we have an excess in the far infrared and sub-millimeter, and this can be fitted with a dust component, and from this you can derive different properties of the dust belt, for example the temperature. So several hundred of these kind of systems have been detected and characterized by large infrared surveys, for example IRAS, ISO, and the Spitzer Space Telescope. And these surveys indicate that about 15% of all Sun-like stars, that is stars of spectral type F, J, and K, main sequence stars of that spectral type, they harbor cold debris disks, so similar to the solar system Kuiper belt. One of the papers that I sent out a link to was this one by Greaves and Wyatt, and they make a general statistical population analysis of the observed 70 micron excess observed in a volume limited sample of 176 stars with Spitzer. And they note that the debris disk fraction is essentially independent of stellar properties. And this means that you can treat the stars or the debris disks as a single population. And in this plot, then, I show you they show the debris disk fraction plotted for 3 different H-bins, and we see that it's essentially flat here. While the actual fractional excess compared to the stellar photosphere vary a lot within each bin. So we have, I mean, although the excess and the amount of dust in each individual system, it decreases with age, but since the initial sizes and masses of the disks vary for each age, we have this broad distribution. So what they do then, they treat it as a single population, and they test this hypothesis by plotting the 70 micron excess against the stellar rank, which is then the ranking of the star in a list where you have the highest excess and then lower ranking or higher rank for lower excess, divided by the total number of stars. And this I have put here. And then they see that it forms a rather smooth distribution, and they make an empirical fit, which is the black line here. And taking into account the transition of the dominant dust removal process from collisional to Poynting-Robertson drag, they also make an extrapolation to lower excess, which is this gray dotted line here. And this then forms a long tail of low excess disks. And the solar system Kuiper belt, seen from the outside, would have an excess of 1 or maximum 2%. So assuming that the Sun belongs to the same population, it would end up here. And this means that it's among the last 10% of the system of the debris disks. So the least dusty system among the 10% least dusty systems. And what implication does this have on the inferred number of comets and possible impacts in the systems? Well, we first want to relate the amount of dust that is observed with the amount of comets. And so the dust is produced in collisional cascades of comets, and dust is also removed. The visible dust is removed by mainly by individual dust collisions in the massive disks, while the dominant removal process is Poynting-Robertson drag, that is drag, photon drag, light drag, which causes the dust to spiral in towards the star. This is dominant in the diffuse disks. So in these 2 different domains, the dust have different dependencies on the amount of comets. So we can skip the details here and just look at the derived masses for the observed population. And it's 0.2 to 60 Earth masses, while the Kuiper belt has approximately 0.08 Earth masses. So this means that the Kuiper belt is significantly depleted in comets. So why is this the case? Well, we should look at the proposed evolutionary history of the solar system. So in order to explain the current architecture Gomez and Morbidelli and some other astronomers from Nice, they made a computer simulation that managed to reproduce the current configuration of the giant planets, asteroids, and comets. And this so-called Nice model also explains the late heavy bombardment that occurred after 700 million years on the Earth and the Moon system. So at that time, after 700 million years, the outward migration of Jupiter and Saturn crossed this 2-to-1 mean motion resonance. And this moved Uranus and Neptune into very wide and eccentric orbits, which practically disrupted the comet belt. So here I have, well, I looked for this simulation movie, which these people from Nice usually show, but if you do a search for the Nice model or the Nice model on YouTube, you find something else. So anyway, these simulation snapshots, they show then here first that you have a very populated planetesimal belt first. Originally it must have been at least 10 Earth masses, and then as Jupiter, Saturn, and Uranus and Neptune. So as these cross the 2-to-1 mean motion resonance, they are Neptune and Uranus are moved into these very wide and eccentric orbits into this belt of planetesimals, and the planetesimals are flung into the solar system and also outwards, creating the current dwarf cloud. So when we are left with just 99% or actually 99% of the comet mass is dispersed, we're left with just 1% of the original mass. So to put the solar system in context then, compared to the population of exokuiper belts that are observed, the solar system has a very small population of comets, possibly then among the last 10% of Sun-like stars. And then when it comes to giant planets, it has been shown from radial velocity surveys that about 10% of Sun-like stars host giant planets outside 3 AU. But the solar system might also have had a very rare dynamical configuration of giant planets, as I showed in the previous slide, that caused this depletion of comets. But if we just assume that these other systems also have terrestrial planets in the habitable zone, so that they have exo-Earths, we can estimate the percentage of solar system analogs and kind of infer what fraction of these of systems that would experience a higher impact rate than the terrestrial planets in our own solar system. So on Earth we have, on average, an impact of a 10-kilometer body every 100 million years or so. And that's an impact that is big enough to cause mass extinctions. So if comet belts and gas giants beyond 3 AU are uncorrelated, this means that only around 1%, there are only about 1% solar system analogs among Sun-like stars. And if they are not correlated, we have the upper limit 10%. So it could also be significantly less than 1% if the configuration, the dynamical configuration of the gas giants is crucial to the depletion of comets. and also, of course, if not all of these systems have terrestrial planets in the habitable zone. However, there could actually be many more systems with low dust content, and hence a small number of comets, many more than Greaves and Wyatt predict, if these systems are not members of this single population that they assume. So that's the impact on impacts. And what's the impact of impacts? Well, there's this very funny program which has a web interface that you can play around with. It's called the Earth Impact Effects Program. It's in this address. I don't know if you can see that very well. I can give it to you later. Anyway, so there you can play around, and you can actually calculate the effects of an impact of a body with a certain size, density, speed, and angle. So in this example, I just assume a 10-kilometer wide comet impacting at the typical speed of 50 kilometers per second, and the most probable angle 45 degrees. And the impact of such a big object, according to the program, what I said before, 100 million years, but they say on the order of 100 million years, so 300 million years. So the energy of such an impact would be 2.44 times 10 to the 8 megatons of TNT, equivalently. Well, major global changes is none. That means that it's not actually changing the tilt of the Earth, the spin of the Earth, or the orbit of the Earth. So the local seismic shaking is 10.2. That's much higher than the highest recorded earthquake so far. The crater dimensions would be 146 kilometers in diameter, the depth 1.33 kilometers. And here the effects noticed in Stockholm of such an event. Stockholm would be, well, I assumed that it hit in Mexico on the Yucatan Peninsula, so 9,000 kilometers away. There would be no direct thermal radiation because the fireball would be below the horizon. The seismic shaking would be felt after 30 minutes. Dishes, windows, doors would be disturbed, cracking walls. And the program here said sensation like heavy truck striking building. I don't know how that feels like. But
basically, you wouldn't be able to tell it apart from the explosion.
Yeah, exactly. So, and after 55 minutes, we will have fine dust and occasional larger fragments of ejecta arriving. The air blast arrives after 7.5 hours, and the max wind velocity would be 11.9 meters per second, so kind of a light breeze, and a sound like heavy traffic. But how, if we go a bit closer to the impact, say on Cuba, just a tenth the distance away, we would have maximum thermal radiation after 4 seconds. The fireball would appear to be the size, 35 times the size of the sun. Flux would be 139 times the sun. The duration would be 44 minutes of the thermal exposure, with a total of 3.6 times 10 to the 8 joules per square meter. And this would mean that vegetation, all vegetation would ignite. Your body would suffer 3 third-degree burns. You would have major seismic shaking after 3 minutes, considerable damage to buildings. The ejecta would arrive, and much larger pieces than the ones here after only 8 minutes. The air blast after 46 minutes, not light breeze, but 389 meters per second. And well, most buildings and structures would totally collapse, and 90% of the trees would be blown down. Well, they were already on fire, I guess. So, what are then the effects? Well, these kind of impacts are possible explanations for many of the recorded mass extinctions during Earth's history. And out of the so-called Big Five mass extinctions, which are marked here with arrows, 4 of them have been linked to impacts, although it's only the one here at the KT boundary 65 million years ago that has shown conclusive evidence. And the possible crater from that impact is this one here at the Yucatan Peninsula. And here in this figure is shown several other impact craters on Earth. Sorry, what's on the y-axis on that one? Oh, sorry, here. So here is I think the number of genera that is extinct. Okay. So then, well, the number of species or whatever in percent, and here is, well, million years. Yeah. So the lasting effects on life could be both good and bad, depending on the magnitude and frequency of such impacts. It could open up new niches and pave way for increased speciation due to higher evolutionary pressure. But it could also, if we have a very high impact rate, say a 10-kilometer body hitting more than every 10 million years, then this could hinder the recovery of biodiversity and keep life at a very simple level. So, should we be worried right now? Well, the current impact threats are monitored by NASA's Near-Earth Objects programs, and well, obviously, the orbits of more long-period comets and objects are not very well known. But so this program, they find new objects all the time, but most of them are less than 50 meters in diameter, so they wouldn't cause any big problems. Well, it would be like a Tunguska event.
Depending where you are.
It depends on where you are and where it is, of course, yes. Well, the data from these programs also suggest that the probability of any major impacts having occurred within the last 100,000 years or so is very small. However, in this paper by Napier, that I also sent a link to, there he shows that several smaller impacts during a short time could be related to an extinction event already as recently as 13,000 years ago. I think this was when the mammoths died out. And that, so he then, and he argues that the cascade breakup of comets when they pass perihelion in the solar system due to gravitational stresses increases the risk of comet impacts by effectively increasing the collisional cross-section. So Earth could run through these swarms of comets and then experience several thousand of these Tunguska-like events in just 1 hour. And I mean, this breakup of comets is well known, and I guess most of you remember this breakup of the comet Shoemaker-Levy 9 in '94, which then crashed into Jupiter, and also last year there was one discovery of an impact on Jupiter.
Is this the major extinction in North America?
Yes, exactly. That's 30,000 years ago.
So this lower picture is actually a recent impact, yeah? On
Yeah, so
Jupiter?
this was last year. There was an amateur astronomer that actually observed this. First he just saw it at the rim, and he thought it could be just another cloud formation or a weather phenomenon. And then he followed up, and then he saw that it was actually like pitch black, and then they followed up with observations with Hubble, etc. And yeah, so it should have been, I mean, of similar size as these ones. but it was nothing that was predicted, nothing that they saw beforehand. I mean, these were predicted, these impacts. Yeah, so then what implications does all this have on the so-called Fermi paradox? Well, first of all, what is the Fermi paradox? Well, it can be said to be the discrepancy between scale, probability, and the lack of evidence of extraterrestrial civilizations. And it's named the Fermi paradox after the famous physicist Enrico Fermi, who wondered why advanced civilizations are actually not already here, since they would have had more than enough time to evolve and spread within the galaxy. Well, for there to be an paradox at all, we have to make some basic assumptions, and that is that the advanced civilizations would actually strive for colonization and or exploration of the stellar neighborhood, and also that the Earth is in no way special, and also that the solar system and the galaxy is not special in that way. And then the third and maybe kind of obvious assumption is that we haven't already been visited by ETs. So actually one of these three assumptions must be flawed in some way. But before we go into more detailed categorizations of these assumptions that Sierkovich does in his paper, which I also sent a link to, we should look a bit more closely on the other side of the Fermidox, namely the scale and the scales. So the size and the number of stars in the Milky Way and in the visible universe is really immense. So we have about 3 times 10 to the 11 stars in the Milky Way galaxy. We have 7 times 10 to the 22 stars in the visible universe. And the age of the universe is, in fact, is 13.7 times, 13.7 billion years. And the age of the solar system and of Earth is 4.5 billion years. And this can be compared with the derived so-called Fermi Hart time scale, which is the time scale for colonization of the galaxy once a civilization has become sufficiently advanced to actually carry out interstellar expansion. For example, using so-called von Neumann probes. So naively, if you compare these times, you would think there would be plenty of advanced civilizations and plenty of time for them to colonize the galaxy. And here is an example of one such scenario, then using these von Neumann probes that you send out, and then they use the local resources of the other planet to self-replicate and then send themselves off to the next planet. And with this method you could colonize the entire galaxy within 4 million years. And then if you compare this colonization timescale with the cosmic timescale, well, have 13 billion years there. And it has been shown actually that, well, although terrestrial planets would not have existed from the beginning, they could have, from dynamical and chemical studies of the Milky Way galaxy, it has been shown that they could have been created already after, or 9 billion years ago, and actually that the median age of a terrestrial or Earth-like planet would be around 6 billion years. The timescales look promising, but the probability of there being sufficiently advanced civilizations depends crucially on these assumptions that we make. So Sierkovich, in his paper from last year, he further categorizes these assumptions into naive realism, which is kind of well, the assumption that the properties that we experience of our surroundings, that we derive from our perception, that they are actually true. And then there is naturalism, which is well, basic working principle of science and the applicability of physical laws. And then there is the mediocrity principle, which he calls Copernicanism, which is then well, the assumption that that Earth is in no way special, and actually that we as observers are not special. And then there is gradualism, which is the progress through gradual change, which basically means that we, by studying the present, can infer something about the past, and the past together with the present, we can make some kind of prediction for the future. And then lastly, there is the non-exclusivity principle that says that we should prefer solutions which rely on a small number of independent causes. And this means, for example, that we would prefer a solution to the Fermi paradox saying that a gamma ray burst kills all civilizations in a galaxy, rather than saying that all civilizations eventually self-destruct. So, with these assumptions, then we can kind of assess the value of different probability factors that would go into some kind of Drake equation, and some recent developments indicate that several of these factors could actually be much higher than we originally thought. For example, well, the well-known fact that we have found more than 400 exoplanets by today, and also what I mentioned before, that it seems that the median age of a terrestrial planet in the Milky Way should be around 6 billion years. Also, that we have found hints that of a very rapid origination of life on early Earth. The discovery of extremophiles. This one is maybe a bit discussable. The naturalistic origin of life and intelligence. The science of exponential growth of technological civilization, for example, Moore's law. The feasibility of, well, theoretical studies of the feasibility of interstellar travel and astroengineering, and also that we have found many galaxies that seem to be Milky Way analogs.
What about feasibility of interstellar travel and astroengineering?
Yeah, so
which are the recent developments? Which are the recent developments that tell that this increases?
well, there have been recent theoretical studies. For example, then this with the von Neumann probes. I mean, if there are somehow if it's shown that the von Neumann probes are impossible for some reason, the timescales are still, I mean, in the upper end of the Fermi-Hart timescale. So maybe not 1 million years, but 100 million years. But still, there should be enough time. And also, they have done theoretical studies of astroengineering projects. For example, these Dyson spheres that can use more of the energy that is available in the solar system. So basically using more of the stellar output energy. So they have done recent theoretical progress in this field. So what are then the possible solutions to the question, where are they, which is posed in the Fermi paradox? Well, the solipsist answer would be that they are here, but that we, for various reasons, just can't see them. And then the rare earth solution, which basically says that they don't exist, that we are very special for some reason. And then the last category of solutions, which involves catastrophes, one of them then being impacts. Well, although it currently seems that the amount of comets in the solar system and impacts in the solar system might be particularly low compared to other solar-like stars, I suspect that we are slightly biased by observational effects. So, since, well, actually, low-mass Kuiper-Belt analogs are not currently detectable. So I don't think that this would be a solution to the Fermi paradox, and maybe we could, everyone, discuss the other possible solutions during some wine and beer and snacks outside.
Thank you, Ricky, for this very exciting talk. I guess that questions and comments will start already here.
Yeah.
Before mine, or
Everyone thinks
I was thinking the effect of the impact, like the Cretaceous Tertiary boundary, didn't seem that severe, but I mean, but the dust from the impact.
Yeah, so the effects I was talking about here were just the immediate effects. Then there are long-term effects from the dust, of course, which
Yeah, shock quartz is found all the way from New Zealand, as far as I remember, so it should have been all over, I guess.
so the dust would have been all over, and killed that. I guess that's what killed most of the life that the sun couldn't. And the climate change, basically.
And it was freezing over, I guess.
And the effects on air traffic.
I have one question.
Yeah.
First, when you look at the infrared excess in stars, what is the level of completeness, especially for stars that have a low infrared excess? You just don't see them because...
Exactly, the low ones. I mean, the ones... the one that they used in this sample was a volume-limited sample, and out to, I don't remember, 30 parsecs or something, and so basically they can only detect down to, well, what is it, 0.8 or so currently. But with the Herschel telescope, they're supposed to be able to detect down to this limit here. But still, I mean, there are nowhere near to be able to detect systems that are as low dust as the Kuiper-Belt has.
But this is effectively a rare earth argument.
Yeah.
In that our excess is in the, there's only 90% of stars have more infrared excess than the sun.
Yeah.
It's probably because you only detect those 90% that move.
Well, that's,
Yeah, so that's the thing.
well,
Here
they do an extrapolation.
they assume that it's part, I mean, that there is no dependence on stellar properties and nothing special with this, that it belongs to the same population. So then I guess it's correct to do like that. But there could be, I mean, this effect of giant planets, etc., that actually says that, I mean, that the solar system belongs to another population of debris disks. so that there could be many low excess systems.
That's a pretty bold extrapolation.
Yes, it is.
And the other question was, so when you look at this propagation of civilization model, I mean, you can have spots in the middle of your galaxy which for some reason have never been reached. I mean, what happened if you apply the same model to the, the Spanish exploration of South America, using horses instead of phenomenal crew? How long you will take for every indigenous village to have been reached by Spanish explorers? What is the probability after, I don't know, 300 years that the village have not been discovered? Because we know that. We have a measure of that. And there are villages which have been discovered 10 years ago, so we have an idea. So you can take that. You can test that paradigm against historical data.
We also have a case where that people are, like, we are looking in a region around ourselves, so our sphere will intersect their observation, their exploration spheres. So like the bigger between a small village with maybe a sphere about 2 miles surrounding itself.
Yeah, but you can try to rescue. You have a model for that. You can try to split the scale.
But the difference in active was already so big, the order of magnitude between the time scale for the reaching one side of the galaxy and the time scale of the stars like.
Yeah, but it doesn't take much with a horse to cross the South America. I mean, yeah, it takes 1 year, but we have 300 years of
Yeah,
experience.
like a lot of problems, we'll never get much efficient with the horse, for example. Well, it's no problem like that when you're throwing the galaxy.
But they crossed on the coast in Amazonas from the west very, very long.
Yeah, I mean,
Building the ships in the Amazonas, going directly to Spain.
Yeah, I mean, so there are several different possible solutions.
What is interdict?
Yeah, so the SU or interdict is that kind of the advanced civilizations, they have an agreement not to reveal themselves to the less developed civilizations. So they have, yeah. So that's that one. And then the simulation is kind of a matrix explanation that we're living in a simulation that has been made by a much more advanced civilization. And then for obvious reasons, we cannot really detect them.
I think that's okay.
Just a question. You mentioned that like 10% of the gas giants are like outside outside three. How reasonable is this value? Because it's like when you measure exoplanets, you normally mostly detect just by the observing limits the hot Jupiter, so big Jupiters.
Yes,
big
exactly.
stars, big planets who are near the sun.
Yeah, so this was from an estimate from I don't remember the paper now, but from several of these big radial velocity surveys. I can look up the reference. I don't remember which one.
So it's not to the future.
No, so this should be.
You can have it up to those planets.
so do you need just Jupiter or you need the net from the planets?
And you can get the flex. I think you can vary.
Because in the models for the depletion of the outer solar systems, you need to have sort of Neptune-sized planet on the outer side of the systems in order for them to be pushed out.
Well, that can.
No.
That you can't detect.
So it's interesting. You're saying two different things here. That there is this rare earth hypothesis, and then you talk about natural stars. I also we were talking about this thing of exponential growth of technological progress in a sense. So now, if you assume that, and naturalists are, then the fact that we are here, we're talking about this, and we are already in a pretty advanced technological state, saying that it's last 100 years it was kind of exponential. I will tell you that this natural hazard cannot be too serious problem unless we are really special, so unless we're talking about an anthropic principle. Therefore, the two things are equivalent. Basically, the rare earth hypothesis and the natural hazard hypothesis are equivalent. So, one to visit tunnel that you really need to.
Yeah, I guess so. I mean, if we have this assumption of the exponential growth.
Unless there is a threshold, which is
Yeah.
very hard to reach.
Maybe that demands one here.
Yes.
Okay, thanks.